Yeah, but I mean, but so like, my impression is the theory is not graphical. So how does it reproduce that? But I thought area scaling was a holographic. See what I'm saying? So proportional A is fine. A over 4B. You can't see that.
It's a real pleasure to have Lehner from Perimeter Institute give us a series of 2 lectures. He's an expert on general relativity, and as you all know, there has been a tremendous discovery made. Finally, people have discovered gravity waves, so Luis will tell us about theoretical aspects of the discovery and further challenges.
Thank you. Thanks, everyone. Thanks for the organizers for the invitation, to the organizers for the invitation. Apologies for not being able to stay longer, but okay, so is life. I mean, as you may imagine, when I was your age, that was 20 years ago, more or less, I think, 25. Yeah, I'm getting older. This all was pie in the sky. General relativity was a punching bag of theoretical physics. Even today, I think we get punched left and right, but we have data now, and this data is amazing. And the field is changing. It's changing in a significant way. We no longer ask ourselves, what do we do when we get the data? Now we're asking ourselves, what do we do now that we have the data? And I think it's a challenge for everyone to reach to that, because the opportunities are immense. And hopefully, in today's lecture, I'll show you some of the connections, and by necessity it's going to be incredibly broad. So at any moment, please do stop me, because I'm going to be going from astrophysics to fundamental gravity to nuclear physics, just to give you some hints of some of the things that are happening. And I truly believe that this is just the tip of the iceberg. As people get more creative with respect to this data, now we have to interpret what is it telling us, why is it not telling us more so far. What are the challenges that the observations are bringing? The ideas are coming from everywhere, and I think we're just beginning. But for that, I'm going to want to take a step back and then just show you one example of something that we have been seeing, or astronomers have been seeing for a while. This is gamma ray bursts. These are, if you've never heard of them, every now and then the night sky, if you want to call it, just go bursting with an incredible amount of energy, something that at the time it goes, it just outshines the rest of the universe combined. Just to give you some sense of scale, every galaxy has of the order of 10 to the 11 stars. We have of the order of 10 to the 11 galaxies. So 10 to the 22 stars, putting their output together, are outshined, but something that goes lasts a few seconds and then it's gone. What in the world produced that? It's very difficult to actually predict and have a good sense of what may be causing it. But the more you look at it, the more challenges are brought. This is an example of one of those so-called gamma ray bursts. This thing here, this tiny sliver, just shoots off in Fermi and Swift. You see this tremendous amount of energy. Then it goes off, and then it turns on again. And for about 100 seconds, it's just producing energy. And if you iterate how much energy came out there, it's about the same amount of energy that the burst had itself. What governs this? Why do we have 2 time scales? What happened in the burst? And how is it that after some time, it turns on again and keeps radiating? We really have no clue. This is another one. It's more speculative. Here you see the main burst. But somehow, these 3 little guys found a way to have a burst before, here, and there. And it lags in the order of a few seconds to maybe 10, 20 seconds. Again, where is that second time scale coming from? we have reasonable models for the main burst, but the second burst, or the sustained emission afterwards, still is a big puzzle. And every time we see something in the electromagnetic sky, or in electromagnetic spectra, we know it has been reprocessed significantly. Light can scatter tremendously with what happened near the inner engine in the galaxy, where this might have been produced, in the traveling from that galaxy to us, and in our own galaxy. And this is very difficult to disentangle. The more information we can add, the better our chances are to try to understand what the hell is going on. These were the shorts. The longs are great questions. So they come in two. This is like, now I'm going to show my age again. There's this awesome Genesis two-part CDs. One was the long and the shorts. There were two different CDs. The shorts are 2 seconds and lower. The burst lasts less than 2 seconds, roughly. The longs are above that. The longs are very well understood. They come from supernovas. It's the short ones, the one we have problems with. And if you want, I can. There is a whole talk we can go about this, and I'm happy to answer more questions. But typically, we also understand very clear differences. And longs are usually happening in star-forming regions. Short are not in star-forming regions, and that begins to tell perhaps a story that it's an older population, the one that produces the short, and this is why people think binaries. Binaries have something to do, and we'll get to that in a moment. But the bigger picture is we've been staring at the sky in all sort of electromagnetic frequency windows, and we wanted to open that one at the corner, which we call the gravitational wave window. And as you know, it has already happened with an observation of the first detection in September 2015. Then there was another one at the end of the year, and there was just another one in January, which was announced last week. I always tell people, even those in Ligo, it's exciting to see what you've seen, but it's even perhaps also more exciting to, now that you know we have the technology to see the signals, everything that we haven't seen is already telling us a long story. And I'll tell you one example as we go along, because there are puzzles in the observations. Another of the differences, why is it that we want to go after gravitational gravitational waves, is that the window is completely different, and the characteristics are very different. Electromagnetic waves are produced by the oscillation of electromagnetic fields, which are due to charged particles moving around. Well, gravitational waves is the motion of the space-time itself, the disturbance of the space-time itself. And the frequencies, once you understand what produced them, are very different. We're going to see frequency gravitational waves from a kilohertz and down by 20 orders. And of course, as you go down in frequency, you're going long in scale. I'm going to show you another graph about this as we go along. With the electromagnetic waves, we're seeing from the megahertz all the way up by 20 orders. So there is this very nice complementarity as to what the scales are that one and the other ones can inform. The main thing I already alluded to, gravitational waves are basically unscattered. So they go through us without any problem. So if we look at the sky now, we cannot see it because photons are scattering off the roof. But gravitational waves will go through without any problem. The main observable in gravitational waves is the field itself, which decays at 1 over r, one of distance from the source. Well, depending on what frequency or what window on the electromagnetic side you're looking at, the signal decays as 1 over distance squared. Of course, in other cases, it's a case of 1 over distance. But by and large, there is a way to gain there. On gravitational waves, we know we can detect in principle from the very early stages right after the Big Bang, while with electromagnetic counterparts or electromagnetic waves, we have to wait till after decoupling. So let's put some numbers together just to keep them in mind. So when the sun is emitting at a rate of about 10 to the 33 ergs per second, and that mainly comes from fusion, hydrogen going into helium. Supernova is 10 to the 42, 10 to the 44, so we've gone at 10 orders of magnitude. And here we are extracting energy from fusion, but also from binding energy of the star. With GRBs, and again, this is part of the question, part of the puzzle, seems to go from 10 to the 49 to 10 to the 51 ergs per second. We see 10 to the 51, But the understanding is that this is an object that is not producing isotropically, because if it were to produce isotropically, there's just way too much energy. You begin to be very uncomfortable with the physics we know to try to predict such a high luminosity if it were isotropically. Everything is much more comfortable if you think it's coming in a narrow region in a jet, and we have evidence for that. But of course, a more radical one would be to catch gravitational waves from the space-time itself, and that's what we're going to be describing today. So, of course, you know general relativity, you have taken general relativity at least to some degree. You know that one of the tenets of general relativity, the most important one, is gravity is seen as not forces by the space-time itself being bent by mass or energy. And one of the main predictions very early on was that light would bend around massive objects. And this is something that ironically was predicted by Einstein with the wrong factor of 2. But he corrected it right before Eddington went with his mission and measured the bending itself. It would have been very interesting if Eddington had done this factor of 2 would have been wrong even after the measurement, because it would have said, okay, this theory is incorrect. So it's interesting just to puzzle as to what a simple factor would have caused in history. But of course, this is like trying to go, I always tease my particle physics friends that are busy at the LHC trying to get new physics. I said, well, look, in gravity waves, at least at the stage you are, there's no way we can lose. At the LHC, you go for the Higgs, 2 things can happen. You either find it where it was supposed to be, or you don't. If it is where you're supposed to be, not big deal. The interesting thing is if it had been somewhere else, unfortunately, it was where you thought it should be. With gravity waves, you cannot lose, because either they are there or they're not. If they are not there, something is wrong with the theory, something is wrong with nature. If they are there, either they're showing that everything is consistent with general relativity, in which case now you have an awesome tool to do astrophysics, or it's incorrect, in which case you're getting hints of gravity being described by a theory that is not just general relativity, it's something else. So far, as I'll show you, everything is consistent with GR, but we're only just beginning to scratch the surface. This is an obvious, very simple plot for you, but I want to make reference to a particular thing. So as we said, masses curve the space-time, and this is kind of illustrative picture, but sometimes it's also confusing. But for black holes, we picture the space-time so curved that there is a region where not even light can escape. But the important thing I want to point out is there is a thing that is called last stable orbit. This is calculation you can do and ask at what point do you cease to be able to have stable circular orbit for particles going around this object. And there is such an orbit beyond which you're just going to fall into the black hole. And this is something we're going to come back to because it tells us quite a bit of information of the object that is underlying the detections of gravitational waves. So some basic things. Tomorrow we're going to push some more on this concept. But let me just take the most basic observations. So stationary black holes are, we believe, are described by just 2 parameters, mass and angular momentum. You could have charge, but by and large we imagine the universe being neutral. So with only those 2 parameters, everything about the black hole should be known. In particular, if we do calculations how black holes respond to perturbations, you can measure multiple moments of the way the black hole decays. And the first 2 are uniquely determined by the mass and the spin, but everyone else as well. So if you measure 3, the first 2 tell you, okay, this is what you expect for general relativity. You can extract properties of the black hole, and then go after the 3rd. If the 3rd one doesn't agree, it's already telling us general relativity is not describing that object. That's something that I'm going to tell you today what Ligo has been able to do, and we're going to challenge tomorrow one conclusion that was drawn after it as to what are the chances that Ligo can go and get the 3rd mode. That last stable circular orbit is this so-called, sometimes called ISCO, innermost stable circular orbit. And it's 9m if you have a particle that is going retrograde with respect to a maximally spinning black hole. It's 6m, where m is the mass of the black hole, for a non-spinning black hole, and is m for an orbit that is going prograde, or it's the angular momentum of the orbit is aligned with the angular momentum of the black hole. And theoretically, you know that you cannot extract more than 29% of the mass of a black hole. So we'll see what is that the detections are telling us. So we're going to be using a few basic properties of how is that we connect signals with observations. So you know that now that we are picturing the space-time as something, as a membrane that can be bent, we need a metric tensor for that. That's a GAB. And if you assume that you're far out from the system and the curvature there is very weak, you can write the metric G as the flat space-time metric, the Minkowski metric, plus some small perturbation, as we're going to call it H. If you put that into Einstein's equations, then you can see that you can rewrite the equations in some essentially a form that is box of H. So this is the D'Alembertian operator acting on your perturbation equal to either 0 if you're far out, or connected with a given source, where T is the stress energy tensor of the source. So far from a system that is isolated, then you just have a wave equation, and this is how we know that gravitational waves are a prediction of the theory. Once you try to tie with the source, then you can ask what would produce these gravitational waves, and well, it will be given by the stress energy tensor, but in particular, it will be the variations of the stress energy tensor, and there is a simple calculation one can do where it will tell you that the strain, that H, will scale like G over C to the fourth times the second time derivative of the quadrupole of the source. So there you notice two things. One is that unfortunate factor of G over C to the 4. That's a very, very tiny number. And the other one is that we need a quadrupole for have any given, any non-trivial strain, and that quadrupole has to be varying. And so then we're going to have to put these things together to say what will be our most likely chance of observing a system. Will be a system that will have the largest possible time-varying quadrupole, accelerated quadrupole, and that will invariably tell us what the main sources are going to be. This is a nice movie, just to illustrate. These waves that they propagate from source to observer are produce shear in the direction that is orthogonal, so they are transverse waves. And this is the reason why LIGO was created in the way it was designed in the way it was. So LIGO tries to maximize the possibility of measuring relative differences in a way that would be orthogonal to the direction of propagation. So if a wave is propagated this way, then LIGO has a laser that gets split at a given central station in two. It goes all the way to the end mirrors. That light gets bounced back. But as we discuss, what LIGO will want to measure is the relative distance, the relative distance or the relative change in distance among these two arms. And the longer the arm, the better or the less of a relative change or the less of a total change you have to measure to conclude there is a gravitational wave. And so they make this laser bounce off this two-hour mirror, and essentially, effectively, in average, bounces 100 times before it comes back in. It gets rejoined with the R1 coming from the other side, and then you get to a photodetector here. And things are designed so that it should be, if nothing has changed the separation distance between a relative distance in the two arms, then they come back with exactly off phase pi's phase difference, and then it should be dark. So you'll hear people in LIGO talking about the dark port. That's the port that will tell them there is a possibility of a waveform. If any light is going through, and you can guarantee that nothing else could have modified the length of these arms, then you will conclude there is a gravitational wave. So LIGO is extremely sensitive. If you run by the detector, LIGO will see it. You're going to introduce enough vibrations on the ground that LIGO will know you're running. I was there sometime in 2000, in the year 2000, and you saw it was a very nice signal they have. I mean, a lack of signal, and all of a sudden there was light coming. And they started analyzing as well. It turns out there was a small earthquake in Singapore. and they can see it. People log in, and in Washington, they actually get a very clear noise that had to do with a nuclear detector, a nuclear reactor that they have down the road, and it produces a very interesting variation. So there is a ton of effort that have gone on the technology side to make the technology catch up to the wildest imagination of theorists, and this guy did it. So we already argue why is it we want to go after, or what are the interesting characteristics of gravitational waves. We do know, and I'll show you on our slides, and something that you already know, that we have detected at least indirectly gravitational waves before, but these were gravitational waves from pulsars that are at very large separations to stars from each other. So they are not really probing very much what we knew from GR doing a good job describing gravitation from solar system tests. So we will ideally, to just try to push a theory the hardest we can, we would like to have cases where the velocities are very close to the velocity of light, and this quantity, what we call the compaction ratio, the mass divided by the characteristic length, where you have that mass very close to 1. So we know that that's being 1/2 is a black hole. Once we do that, or that was the promise, we could say something of the population of black holes, of which we only had indirect evidence till the detection. We would know more about neutron stars, masses, spin, locations, the behavior of cold nuclear matter, cold matter and nuclear densities, and hopefully, by joining the electromagnetic and gravitational wave windows, we will learn a lot more about many interesting systems, and in particular, surprises. And these surprises could be in many ways. Could be surprises as to, oh, there are deviations with respect to what the predictions of general relativity are. There are interesting puzzles on the astrophysics front, etc. And I argue we already have some of those puzzles already with the detections we have. So, okay, that I already covered. So we want to know about a whole bunch of systems out there. In particular, we know some of these systems will not produce electromagnetic counterparts. And it all goes down to this. If you're looking for something in the detector, the detector is as good as the detector is, there is a noise level that is significant, and you're going to have to dig the signal out of the noise. And that introduces a very important role for a theoretician to play, which is to tell the detector what to look for. But that's a challenge as well, because LIGO will not be able to go after things you haven't told it, and as I'll argue as we go along. So LIGO cannot see something that we don't know how to look for. So let's put some numbers together. Imagine you have an object that has some given mass m. It's under has some characteristic length r. The frequency, the natural frequency, the numbers you can put just based on the natural quantities in the problems, will scale like the Newton's constant and the density to the 1/2. The quadrupole, given that frequency, this acceleration will go like the frequency square, the mass times the r square. And the strain will come out just to be this combination, which actually is very interesting. It's just the potential, the gravitational potential from the source at the source times the gravitational potential from the source measured wherever we are. So of course we can do nothing with the first term. So with the second term, we're going to be as far as we have to be given what nature has to provide us. But in order to make the strain the largest possible, we want that number to be very close, as large as possible. And as I said, the largest we know of are black holes. Yeah, you're assuming just a standard virial thing. Of course, you're going to get a boost, hopefully, close to the merger itself, but this is just some back of the envelope estimates. And these are the arguments that you had to put, or you had to make early on to sell it to an SF. And I'll say a few things about that. So the luminosities, well, the luminosity is huge, provided we have the right source. And if you say, well, suppose you have an equal mass binary, and I'm going to keep making this example as we go along, that is sitting 15 megaparsecs from mass, as 2 neutron star, and this goes to what I was just telling Daniel, LIGO was built thinking of binary neutron stars because those were the sure sources. We have identified, or people had identified, of the order of a handful of binary neutron stars that will merge within the Hubble time. And so we armed with that, they said you can go to NSF and said, well, give us the money. We can really go after something that we know is there. And this is why these numbers are together. So if we have 2 neutron stars that have total mass, of, say, in each one of 1.4 solar masses, that are lying 15 megaparsecs per mass, and the separation of them is the order of 90 kilometers, then the strain is 10 to the minus 21. We need to target that. We need to reach that target. And that's what LIGO worked very hard over many years to get to. And they finally got to it. 4 sources up to maybe of the order of 60 megaparsecs for the right sources. And I'll say more about that as we go along. In 2015. The frequencies, notice the frequency, well, up to some proportionality factors is 100 hertz. Again, this tells you why LIGO has the same shape it has. They worked really hard to have LIGO have sensitivity from about 10 hertz to about 1 kilohertz. And that's because of that. And then you can estimate how long would that binary stay within the window of LIGO, and it's about half an hour. For the right masses, or for those masses I put there, he asks how long it will take for that binary to go from 10 hertz to about 1 kilohertz. That's where LIGO actually gets to see this object. It's about half an hour. This is great because you have sufficient time, if you have the right tools to do the analysis, to perhaps go after the signal for the first 20 minutes, analyze it, and then tell observers within 3 minutes, point in that direction of the sky because you're going to have the 4th of July fireworks. It will be the first time ever in astronomy where you know something is going to happen before it happens and you tell people, go look there. We're going to see if LIGO can actually do that or how far they are from doing that. So I already alluded to this case. This is the binary pulsar that was the recipient of the Nobel Prize in '93 by Hulse and Taylor. And this was a ridiculously good measurement, right? So here you see, I think there is even a bit more data. The prediction of general relativity using just some given approximation, which we're going to discuss later on, to this parameter. Remember, we had this parameter, it's compaction, m over r. There's a way to have a perturbation scheme that keeps track of these terms. So at this order is where gravitational radiation reaction comes into the game, and you can calculate what it should be the rate of change of the period of a binary pulsar. You get to see a pulsar, and just by following how perhaps faster you get to see the signal coming to you, you can infer that the orbit has gotten tighter. And the prediction is the solid line, the data are the points, and the points have the error bars, and they are already exaggerated in the picture. But okay, so now that you say we're going to go after these gravitational waves, if you actually think this is a worthwhile endeavor, you can ask, okay, what type of sources can we see? That's a very accurate measure, but it can't see further down because they are too far. And unfortunately, we cannot see them anymore because there is precession, and so you don't see the pulsar anymore. Yeah. Or if it's not gone, it's about to be gone. It's already making it very difficult. Yeah, it stopped because it precessed, it went away. There was another system that was found a few years ago that was a double binary pulsar. You actually saw 2 pulsars, but they precess away, so you cannot see them anymore. So remember, as I said, as you change frequency, you change the length scales you're probing. So LIGO is probing this region from a kilohertz, from 10 hertz to a kilohertz. But if you think what other sources should be out there, well, one is supermassive binary black holes. We know galaxies in the picture of hierarchy structure formation of the universe, galaxies merge. We now know that every galaxy that deserves its name has a black hole at the center of the galaxy, and we're going to connect back to this idea of where it's in the center of the galaxy and what does that mean. Eventually, galaxies merge. Those two black holes should come together, though there is a very interesting question out there, the so-called last parsec problem. We don't understand well the physics to make sure that they actually come together close enough for radiation reaction to take over, but we have no evidence observationally that these black holes don't have a way to cross that the stage. If you want, like, we can elaborate more on that. But assuming there is no problem for these black holes to come together, then you should be able to see them, and this is this plan of the so-called LISA interferometry observatory in space to actually go for those. And these are black holes with millions of solar masses and above. You reduce by a lot, but then LISA, so now LISA is out there, so the scale of the separation is of the order of millions of kilometers. There is essentially no noise, and the redshift at which you could see is extremely far. And so then you actually get a very decent, I mean, it's supposed to have many, many more events than LIGO. Yeah, but we need to fly it, right? And for many years, that was a big question. That's actually here. So H, you can see it at 10 to the minus 18, these objects will be measuring. We also have this very cute idea, which actually is almost doing everything for free, which is to go after the same, essentially, similar type of binaries, supermassive binary black holes, but not when they are merging, but when they are some distance apart, where their orbits of the order of 1 year. There you can use, remember LIGO uses lasers, same thing as LISA, to send a laser light, it goes to the two arms and then it comes back. But if you have a whole bunch of sources out there that are telling you very clear timing signals, then you can check where at any point that time of arrival of pulses have gotten shorter or longer. If that's the case, maybe a gravitational wave went by. And this, the pulsar timing array, there is a little bit of noise that is happening as we speak, where they might be getting extremely close to having enough data to actually say something about whether they are seeing some background noise of supermassive binary black holes going around each other. That might be a bit premature, but it's something that will happen within the next 2 or 3 years. And of course, then cosmic microwave background, but after BICEP, I'm not going to say anything. Just the orbit. For the right, so wait, with LISA, you see the coalescent. Absolutely. Many. I mean, I can look at the numbers, but many. So the LISA estimate is that it'll have a signal every day.
They'd be able to see other events, or is that like a graph as two galaxies hitting each other every day?
That's once you see this far, you're actually seeing the byproduct of two galaxies having hit. And then it takes a long time to. But that's a great question. The other source that it'll have is a nuisance. White dwarfs going around each other, a binary of white dwarfs produce gravitational waves in the same frequency. If they are galactic, the strain, even though it's much, much weaker than two black holes coming together, of course. If they are galactic, they're just way too close, and they produce a background noise. And so then there are interesting possibilities. You know, there's the old saying that someone's noises is someone else's gold mine. And there are lots of interesting ideas how to go after that. So I say the strain decays 1 over r, but increases with total mass and separation. So the closer they get, the stronger the signal it is. We're going to see this. But we also pay sometimes a price for mass ratios that are different. Then the intensity of the strain also goes down. So imagine Q, in this case I imagine that M1 is a larger mass, M2 is a weaker mass, so Q is a number that is lower than 1. So then you have this correcting factor for the same object, for a same binary of the same given mass. If there is a mass ratio, you actually get a lower sensitivity. And that will imply that if you have, say, a mass, fixed mass, I imagine that M2 divided by M1 is 1/2. So now 1/2 will say that the signal coming from an equal mass binary, you can see twice as far. If you can see twice as far, your volume is 8 times as large. So this is not going to be, keep that in mind, because this will imply something about what the types of sources LIGO has seen. You're going to, something that could have appeared surprising at the first sight, it actually turns out not to be. So how do we get there? We want to go. So first you get someone to pay for an awesome instrument. So NSF did that. And also Europe, but that telescope is still, or that observatory is still kind of struggling. They should be joining maybe sometimes this year or in the following run. You have to be ready to be able to dig out the signals from the noise. And last but not least, the most exciting thing is just understand how you can get the most out of the signals you get. So these are some pictures. So this is the example of what I was telling before, this pulsar timing array. You get signals from all your pulsars, and by analyzing the time of arrival over a decade, then you can begin to use every pulsar to see if there is any residual in the time of arrival. This is an artist's conception of LISA, and it's an exciting plan. So far, every detection has been seen. So it's been done with the Washington and the Livingston sites in the US. But down the road, Virgo will join. GEO is a German detector that usually is not competitive. Its arm lengths are much shorter, but it's where most of the technology goes and is tested first. There is LIGO India, that the plan was that it would happen a lot earlier, but now it's probably 2023 or 2024. And Kagra in Japan, they're going with a very aggressive schedule, and they might join in the next couple of years. Why do we care about having more than 2 detectors? Because localization in the sky is done by triangulation, which is time of flight difference between the detection facilities. And this is what I said. Remember, in this very kind of optimistic picture, you analyze the signal for some time before the merger takes place, and then you tell the observers point in that direction. This actually tells you what really is a possibility. Depending on how many of the detectors are online, then you'll get better and better in sensitivity. But for astronomical standards, it's still very bad. Let me imagine this case, binary neutron stars, and then you ask, what is the percentage of the detections that you've made that you'll be able to pinpoint in the sky within a window of 5 square degrees or a window of 20 square degrees? So it's 17% by the time we get all the detectors together, or 48%. 20 degrees or even 5 square degrees is huge. It's a big chunk. It's not competitive at all with astronomy, but at least it gives you some guidance. This will get better with time, but we're just starting. I mean, there's a long way before we can actually tell you exactly where to look. And of course, there are many detectors in the planning stages that actually will do that. So let me just turn into the detection strategies, because this is where much of my work has been going. So this is a picture of the estimated improvements in the LIGO detector in this generation as time goes by. So LIGO is right now roughly where the green line is. What they are measuring now has, depending on which detector you're talking about, is of the order of 70 megaparsecs. Whenever they tell you distance, be careful. Usually when they tell you distance is based on 2 neutron stars of 1.4 solar masses together. Of course, we know that LIGO detection has gone much further, but that is for a different source. But it just gives you some ballparks. It's like the standard meter. So the standard meter is 2 neutron stars coming together, and for them, LIGO is measuring today at about 70 megaparsecs. And eventually will come down by a factor of 3. And again, a factor of 3 is a factor of 27 in volume. So whatever you see now, imagine it being 27 times more frequent. So how do you go about trying to dig the signal from the noise and eventually also get the physical parameters? Well, the technique of choice is this thing called match filtering. So what you do is you have a bunch of templates. So from theory, you say, this is what I would expect if this particular system were to go together, and then you do it for every single thing you can imagine. You do an inner product of what the detector data stream is, which I'm here calling D, with that template, and you actually have to shift it in time, because you don't know when is it that the binary came together, or you don't know when the binary came into your frequency sensitivity band. And so you also have that parameter as an unknown. And then you see which one maximizes this inner product. So it's an inner product weighted by the noise of the detector. So you're going to have much better sensitivity here than at low frequencies or high frequencies. The good thing of that is that if you have a very good match, then you can ask which of the many, many templates you had gave you the highest possible match, and from there you extract the physical parameters of the source. Of course, this is, as I said, bad if you're trying to go after some surprise, because if you didn't tell Ligo what to look, and there was something out of the ordinary, how are you going to go and distinguish it? So fortunately, there is another way. You just use the fact that you have two detectors, and you see if there is something that happened to have gone in the one detector. You ask if the other one saw it in coincidence or with some lag time, given that the two detectors are some distance away. And then you just see if it has the right properties for something that when burst. With that, you can do a lot, but you cannot see as far as with this one because you're not using as much information. And at the very end of the day, you cannot answer back what was precisely the source that produced it. So this is an interesting possibility that is actually done all the time, but will not tell us what the source is. Might at best tell us, oh, there is something very weird, because we don't understand how any system could go and do this, but that's all. So now let's think about how do we go about giving that information, the theoretical information. So typically you would expect, very roughly, 4 stages in an spiral. First, there is something that we call the Newtonian stage. It's something that if you look at the system, it will take much more than the Hubble time for the objects to come together. So either you find a way to invoke, there are other mechanisms that will bring them together, and I'll show you one example as we go along, so that once they get sufficiently close where radiation reaction takes over, you can check if such a system will merge within in less than a Hubble time, and then you can go on. If they are sufficiently close that the system will merge within the Hubble time, but still not so close that strong GR effects will have a significant role, this is where you can do this so-called post-Newtonian expansion, where the Einstein's equations can be recast in a way that is Newton plus Newtonian dynamics plus some different corrections that involve kind of spin orbit correction, etc. And radiation reaction comes at this order, so it's m over r to the 5th power. And then you can ask the question, at what point could I begin to tell a black hole from a neutron star, or from an object that is not exactly like the black hole in general relativity? Unfortunately, that comes further down. It comes at m over r to the 10th power. So this is very delicate. It says that tidal effects or anything that will tell us, oh, this black hole happens to have a structure around it, if it is very close to what the putative event horizon would be, it would be very difficult to disentangle. And I'll show you some examples. And by and large, eccentricity is not seen to be an important ingredient because of the properties that gravitational waves tend to circularize the orbit. But in some possible formation mechanisms, eccentricity will be important. Then they get close enough where the velocities involved in the expansion are close to the velocity of light. That's when you need to do numerical relativity, or just relativity, solve the equations in full. And unfortunately, we don't have a good way of doing it in pencil and paper. I swear to God, if I could do it with pencil and paper, I would do it. I am not someone who loves computers by any means. I will always try to do something else if I can avoid doing a computational simulation. But when you don't have anything else, what can you do? So this is a picture just of one of simulations that shows two black holes coming together. This is a very early movie. You don't have such a lot of fancy visualization in it. These were two black holes that had equal mass and they no spin, and they come together. You can see what the final relaxation to the black hole is. You can ask what is the final structure of the black hole spacetime, and it tells you, well, if you merge two black holes of mass m, Your total mass would have been 2m if you didn't radiate any energy. You ask how much energy they radiate, it's of the order of 4%. If you ask what is the final spin of the black hole, well, it's of the order of 0.67. If A, remember, is a parameter of the Kerr parameter, A over M is 0.67. That number will come back. The gravitational waves, that's a picture. So initially you have some bursts of radiation because the initial data is not exactly the one you would like to have. If you knew it, you wouldn't be solving the problem. But then the orbits actually take over. You have exactly what Einstein's equation should be telling you the solution should be for two black holes coming together. Then you have the burst of radiation when the merger takes place, and then it quickly relaxes to nothing, and then you begin to see some structure which is just numerical noise that is very self-leading. So, yes? Beautiful. So that, I'll tell you, let me just tell you right now. So effective one body, and this is something that a posteriori was understood, and tomorrow we're going to discuss more. Why is it that that might happen? Let me just describe that, and I'll answer to your question. So if you look at that waveform, this is actually a similar system that was slightly higher separated, wider separated, so that we have more orbit. So initially you have that burst of radiation. That was that noise of, we don't know exactly what the initial solution should be for two black holes at any given time. You got something that's consistent with Einstein's equations, and you let it go. That it's called junk radiation. It disappears or goes away from the grid very quickly, and then you have the true physics. Then it keeps going. This is in spiraling. And at some point, the merger happens. It used to be that people would say, well, maybe here it could be very, very complicated, because after all, you're perturbing the space-time of one black hole with another object that is exactly the same. All sort of crazy things would happen, but then this is what happens. So this is zooming in here, changing the scale, and it's very smooth. If someone had put a gun on our head back in the days where we couldn't do resolve this problem, and he said, tell me what you think your best guess of the waveform would have been, this is what you would have written. Because you'd have said, well, the smoothest possible matching between the in spiral that went turned well and the after merger, which is described by a black hole that has been perturbed, that is decaying to a Kerr solution. This is what you're saying. So a posteriori, once we understand things are, of course you could do it before by fiat, but now that we know this is what the theory has in store, here is where you can say, well, I can use an effective one body. And there are lots of claims out there, I'm not going to say names, that, oh, we have the best EOB model because it's analytically derived. I think all this is bull. They're all more or less the same. There are even better ways of doing it. But once you ask anyone how many free parameters you need to match the early part with the late part and do a good matching with what numerical relativity is telling you, all those approaches need more or less the same number of parameters. 4 or 5 things to be adjusted by numerical simulations. So if we use our Fino hat, they're all the same.
So basically what you're measuring is just oscillation around the black hole.
Yes, and the transition. Oh, and that's what I meant to say. You can ask when this transition happened. So what point did you go from the in spiral into this? Remember the last stable circular orbit that I mentioned? Which can only be defined kind of in rough terms for equal mass objects. Turns out that you can do it and gives a very perfect natural way of doing the transition. So the two black holes are also describing something that at some point you can imagine also taking the limit of one of the masses of the black hole being very small, and naturally you will connect with this regime, for the test particle regime. If you scale from there, you get pretty much this, to within a few % error. There was a question there.
Yes, how many filters are there in the sense that there's an enormous number of ways things can possibly happen, different mass ratios, different angles at which you get.
Sure. That's a very good question, and I'll show you a few things there. But that's a great question, and it means the strategy that you go to after trying to do the detection varies. And there are several layers, so there are some analyses that are rather crude, trying to see if you can identify something rather quickly, and then there are things that take a very long time because they go much more refined in the template filling and then they try to see where. And this is the reason why some signals you get to hear rumors right away, and some others you hear kind of some kind of noise in the background. Slowly, it's either builds up or builds down, and it's because I go through this analysis. Ligo, as of today, or as of last week, have produced 6 triggers. Going very crudely on the data, they have identified, there could be 6 signals. But caveat could be that they're all noise. They send it out, and of those 6, 1, they put a paper out last week. There are ones they're still working on. And these were January, right, some of those? And there is a lot of effort there. So I'll show you some things tomorrow, just in case you're interested. But I'm going to spare you the details of how you go about trying to do these numerical calculations. If you want to look under the hood, okay, all codes, we should have something that encodes Einstein's equations. And maybe if you want to explore some alternative theory of gravities as well. If you have matter in the problem, okay, you have to wonder about hydrodynamics. But the matter described in the star is probably magnetized, so you need magnetic hydrodynamics. But outside the stars, there's a plasma, there's this pulsar. Just as analogous to the pulsar magnetosphere, so there is a magnetosphere that may actually be very important in channeling possible electromagnetic counterparts. You have to put all that. We wanted to answer the question, what is the equation of state of Newton's star? So we don't know what the true equation of state is, so you need to parameterize and get some very interesting information coming perhaps from nuclear physics and tabulate the equation of state. And these are examples of 3 the mass-radius relation for 3 very natural equations of state that come from nuclear physics, so you have to study all of them. In fact, there are many. You also know that when these objects come together, if you got 2 neutron stars, the temperature just goes to hell. You can lose a lot of energy through neutrinos, so you need something to do that. So that is where kind of general relativity meets the whole of physics that is classical, and then you have to somehow face the music and bring everything you can together. So what did the simulations tell us before any detection? I'll show you. So if you collide 2 black holes, let's say and they are sitting at 10 megaparsecs, the relative change in length would be 10 to the minus 17. So it's much, much larger than 2 neutron stars. The peak luminosity happens to be 1/100th of the Planck luminosity, ridiculous amount. And depending on how you choose the system, where you have spins or not, you can radiate from about 3% to 12% of the total mass of the system. One surprise that happened to be obtained from numerical simulations is that as you radiate energy, if you have an asymmetry in your system, for instance, a mass ratio or spins that are misaligned, you end up, imagine an orbit. After an orbit, you radiate more net energy, more flux of momentum in a given direction. But the center of mass in general relativity has to be conserved, so the final black hole will recoil in the opposite direction. So once the merger happens, for the right configurations, and granted those could be fine-tuned, you could have a recoiling black hole that is just moving in the opposite direction with a velocity of several thousands of kilometers per second. That's very puzzling, because that's much larger, or significantly larger, than the velocity you need to dislodge an object from a galaxy. So remember we said that you could have 2 black holes, supermassive black holes, that were black holes at the center of galaxies that then came together, and that we don't have any evidence of black holes that are off-center. So somehow nature doesn't like these situations. And so this is one example of the lack of an observation is already telling us a lot about what nature may have in its store. Let me just, no, I'll tell you about more things about this tomorrow. Another thing I mentioned before is when I make the difference of, remember, if you have a mass ratio, the distance at which you will see an object gets shorter. The same thing happens with the pattern, the internal pattern of gravitational waves. It can see, so if you have an object that is colliding, say, and the orbit is in this orbital plane, you get to see a lot further if LIGO were to be there than if it is to be there. So as a result, we are more sensitive to seeing things face on than edge on. And remember, any factor gets cubed, so it's not surprising. Once we begin to see what is it that has been seen, the different type of scenarios or systems that we have already obtained. This goes to someone was asking this question, I think your question. So this is another case. Suppose you actually think that the objects are spinning. If the spins are not aligned, there is spin-orbit coupling. This spin-orbit coupling makes the orbit just wobble. But now you can say in which direction, if you see an the waveform, you'll see the most difference. So this is, let's say, the gravitational wave train of two objects that have some given mass, but no spin whatsoever. The next one is two black holes that have some given mass, but now have angular momentum, but we just happen to be observing in a way that is along the direction of the total angular momentum from the system. And we see no difference. Essentially, there is no modulation. But now just tilt yourself a little bit, and now you see this modulation, that and that. So if you are exactly a 90-degree angle with respect to the total angular momentum of the system, there is tons of modulation. So this would be great, because this is what we would need to understand the individual angular momentum of the black holes. But as I already told you, we're less sensitive if we see things from the side than if we see things from the top. So these will require more signals, and then some small subset of those will begin to show this. To date, we don't have any evidence whatsoever of this modulation. But it could be just selection effect. Okay, so let me just begin to go into reality. So that was the first signal, which if you want, there's a very interesting story there. It was lucky in more than one way. The first one, you got to see it. There was no need of detection templates there. The guys just saw it as the data was coming around. So much so that the first reaction of the people that saw it is, someone screwed up. Ligo, as opposed to, say, the LHC, where they can turn off the source, and you can actually check what is the background noise of your detector, Ligo cannot turn nature off. And so what they do is, every now and then, they inject a fake signal. They don't tell anyone, and then it's there. Sometimes they don't even know they're doing. So they push a button. There is a random number generator that decides where the signal is going to be sent, injected or not. They go through the analysis, and then they check whether they were able to see it or not. And that's one integral part of their analysis. So their first reaction is someone screwed up, because it's just too massive. We were not expecting two black holes of 30 solar masses.
How many people know if it's fake or not?
So as I said, they, even themselves, so there's just 2 or 3 people that know that they had pushed a button, but they don't know if the signal was put or not. There was a few years ago, maybe 2013, where they actually went, they saw the signal, everything. They even got to the point of writing the paper and uncorking champagne, or pulling out the champagne from the fridge, and then they opened the envelope and say, oh, no, it wasn't. So very quickly, but just checking at what point you had the highest frequency. Remember, the highest frequency, you would imagine, is just at the point where these objects are going the faster around each other. The acceleration of the quadrupole is changing the fastest. And then they just go merge on. So you can very easily, just from that observation, say, oh, this is the frequency at which it peaked. I kind of guess what the final mass is. And this is where it said 59. Are you kidding me? 60, this is not true. And then they went through the full analysis, and there it was. So it was very important, and this goes back to your question earlier, because the initial templates did not account for such large masses. Had this not been there, at the distance at which you will see it, maybe people wouldn't have said, oh, we need to enlarge our parameter space. So that was it. Then you can compare general. The other thing is that they can use also the wavelet reconstruction, no GR whatsoever, and get very much the same signal. You can take the raw signal from the detector minus some noise widening. You take the difference, and then you see the residual. So it's very good agreement, except once you come here, because this is kind of normal in normalized units. This is the signal went with a strain of up to 1. The error here, the residual, is 0.5. So you say, well, how am I to believe that this is true when the residual is 50% of the signal? Well, this is what they do. They look elsewhere. If you look before or after by a long time, this is always consistent with nothing. While that one is the fact that it was there. They said, well, the residual or the noise, the background noise of your detector is of this type. This was about that noise. So that's was done. Well, they convinced themselves that it was real. If they check.
No, I mean, this happened in Louisiana and in Hanford simultaneously.
No, there was a phase lag. There was a time lag, 7 milliseconds or so. 7 seconds or so.
The appropriate one.
Yeah, the appropriate distance.
There's no chance someone pressed it.
That was the second thing. So first, after saying, oh, someone screwed up, the second thing they worried about is someone hacked us. And maliciously put, so they went forever. So there is a very nice talk that I'm not supposed to have seen, where, this person, it goes at length of every single test that they did to make sure that no one had went in from the outside. There were people that were cornered in rooms and just kind of, there was a cross-examination, everything to make sure that this was not there. Okay, once you do this analysis, you can also tell, okay, what is the likelihood of these signals? And so 5 sigma. I can go into the details how you get that, but the point is that they go at length to make sure that it's significant. Then there was this other one. I'll tell you what the parameters of the source are in a bit. There was this other one. This was in much lower. This was under the noise, so they couldn't see it. That's just kind of the signal. The best matching signal is overlaid with the detector's noise, and then you actually see nothing. But in the background, this inner product you're doing is slowly building up a signal to noise, and this is how they convince themselves that it's something. Right? After some time, you actually build up enough confidence in the signal, and by the time you get to the merger, you have gotten an SNR of 10 or thereabouts. Ligo has that criteria for a false, for qualifying something as possible, an SNR of 8 or above in each individual detector. So this one cleared that test.
Wait, they triggered on a signal that was smaller than the noise?
The signal is buried in the noise. That's the R1 was a crazy one. No one expected the R1, that the signal would be above the noise. This is what you think is going to happen all the time.
The signal to in general be below the noise.
Yes, and you can make that very basic calculation and say, well, if it is this megaparsecs away, it's going to be in the noise. Because the noise is of the order 10 to the minus 21. And this is the one that was announced last week. I'll tell you the parameters in a second, but it's like the first detection, but twice as far. So it's another case where you actually don't see it if you don't do the analysis like the ones I mentioned. But both the one using the GR templates and the one just basically trying to fit some exponential sine Gaussian behavior both pick it up. So this is by the middle. This is a picture from Ligo. This is what they have. It's a nice illustration, but of course we know better. So let me just show you what we know today. So we have 3 signals plus something called a trigger, LVT. Incidentally, just as a funny comment, that everything that is a signal is called GW, year, month, day. But after they put out the first paper, they got a complaint from the International Astronomy Union that nomenclature was already taken. It was for galactic worms. I'm not kidding. This is something that in the 80s, when people were looking at radio images of galaxies that were kind of edge on, they will see some filaments, and okay, looked like a worm, but they decided to ignore it. So notice the probability of the 3 signals. It's about 4 sigma. What we have here, this third and fourth column is the masses. So the first one is 36 and 29. The next one is 23 and 13, but that's dubious. 14 and 7, 31 and 19. So people ask often, look, we saw 2 30 solar mass black holes, and they are not too dissimilar in masses. Is this surprising? Well, you now know it's not, because you actually get to see much further those type of objects than those that are that have a much higher mass ratio. At some point, we're going to get to see those. This is a very interesting number, the one I like the most. Remember, unfortunately, I don't have the number. This is essentially that number. This chi effective. Let me just tell you the story first. When that signal was seen, and then the decay rate of the ring, the signal was measured, the spin was inferred. And what do you think the spin it was? 0.67. Remember I told you that number 0.67 was the very first spin ever measured in the collision of 2 black holes in a simulation, that there was 2 black holes that had no spin, equal mass coming together. When I saw the paper, again, which was leaked a week earlier, that was my first reaction. Is what the hell? How is it that nature just provided black holes that were almost the same as the first one we understood? That's an interesting question, and it's actually calling for some, when more data is available, for some interesting answer, and I'll show you, and I'll say a few things. This chi-effective is the measurement from the waveform you can get of how much spin is aligned with the final in the initial configuration, aligned with the final angular momentum of a black hole. Notice that it's 0.06, 0.0 minus 0.2. It's a very small number. You could draw two conclusions out of this. First, that there is not significant spin in any way aligned with the final final angular momentum. So this is a strongly disfavored case. So you can say, well, how else? Because the total contribution is essentially zero. That's what these numbers are saying. So I say, well, maybe I could do this. Well, what are the chances that nature provides that? I mean, this is an unstable configuration. There are torques in the system. Of course, you could have this. So LIGO can say very little because there are no modulations of how much spin is in the orbital plane. For that, you need to see the modulations. That's going to be hard. It's going to take more time. But one possibility, maybe the most conservative or the craziest one, is that they don't come with spin. And if that's the case, what the hell? How does nature do that? That needs to be understood. Because there is very little spin. One possible out there explanation is that maybe interaction with putative dark matter candidate particles like axions, where you can have an interesting effect where angular momentum from the black hole gets extracted by the scalar field itself, can actually deplete the spin of the black hole. We have and this is an idea that is out there. This is something that Asimir Vanitake, Masha Parashar, Robert Lambie are pushing or are exploring. So far, we have very few detections to say that that's a strong possibility. But if we keep seeing black holes that keeps getting this configuration, this type of answers, we're going to begin to say, maybe these guys are onto something. Also, remember I said we have to be very mindful of the things that they don't see, because now now that we know that if the detector is on, they see the gravitational waves. You can also ask, what happens if you have this configuration of black holes going this way? So the final black hole spin is higher if you have this. If it is higher, we go much faster. If we go much faster, we see them much further. So the fact that we haven't seen them also tells us nature doesn't want this. Why? And so this is what I'm saying here. I think there are enough questions or puzzling features that of these 3 or 4 signals, plus what we haven't seen, is already calling. So one of that, he began to push bring some tension in the formation mechanisms of binary, compact binary objects. The most loved one that people had in their arsenal was this thing called the common envelope model. Let me just show you a picture of it, which goes more or less like this. You have 2 massive stars. One of them begins to puff up, and this is something natural that stars do, unless something else happens. Typically, this is what our sun is going to do. Eventually, it's going to eat us away. So you have one that grows. It transfers mass to the other one. Eventually goes supernova. Now you form a neutron star of a black hole. Now the second big one begins to do that. It grows and it eats up the black hole. Now it's as part of the common envelope. This is why it's called the common envelope. Why do we need this? Why is it that people bring this kind of controlled picture, if you want? It's because of what we said at the very beginning. If this didn't happen, the stars would not have a time to merge within the Hubble time. So you need some mechanism to bring them together. And the envelope is doing that. Interactions, viscosity with the envelope is drawing angular momentum from the tiny binary into the envelope. Eventually, the R1 goes supernova, blows the envelope away, and there you have 2 neutron stars, 2 black holes, or a black hole neutron star. When you look at the calculations done in this model, you actually don't have a great chance of forming 2 black holes that have large masses. So this first observation challenged this. Not so much because you can still adjust it after the fact by changing the metallicity, assuming that the metallicity is sufficiently low that winds will not strip a lot of mass from the star. So there are ways to make it fit, but it made people uncomfortable. Also, you have formed things in objects that was in a binary. The common envelope is also going in the binary. If anything, you're going to have spins that are like that. Again, that's putting some tension, which you can accommodate, but it's already interesting that we have it. So after this happened, or some people would say, while this was going on, before the paper came out, some people took wind of this, and they came up with another model. That's kind of induced publication, I would say. It's called the chemically homogeneous model. Now you picture that the two stars, rather than being at the natural distances originally, they are much closer. Because you're much closer, they interact a lot more. There is a lot of convection. So this puffing up of the star is disfavored because there is chemically mixing due to convection. And rather than going red and puffier, they go blue and they get much, much tighter. Because you started them very close, they have no problem producing, accounting for the very large masses, but it do also would predict very high spins aligned with the orbit. So again, this is putting some pressure. Dynamical capture, that says, okay, you have a very active star formation region in global clusters. You form these black holes, and eventually they get captured. This could have completely arbitrary, randomly oriented spins. So it's fine. So the last signal, the one that was seen here, because it's favoring kind of more strongly spins in the opposite direction, which is very, very difficult to accommodate with the previous two models, it seemed to be giving more support to this capture as opposed to the other ones. But again, we're doing statistics of small numbers, but it's interesting to kind of foresee the discussions that will happen as more gravitational waves are detected. So now what do we know of black holes? We knew by indirect evidence a whole bunch of them which had low masses. This is in X-ray binaries. And now we have, this is where you get to count in the way you want. So this is like when you're an accountant, whatever suits you. So you can say, okay, we have 6 black holes, we have 3, or we have 9. Because you have 2 that came into 1. So now Ligo has told us about this. No, this is real data with a model. Well, there are a lot of questions related to that. So this is X-ray binaries. So this is an electromagnetic observation with a model. The model says, okay, you have an accretion disk, you're fitting in a particular way, and you have to adjust a few things. But there are, definitely interesting, robust features in that model. We tend to believe it. So this could be a completely different channel formation. Also, these guys seem, when you actually measure, they have spins. Many of them have spins and have relatively high spins. And these ones are not showing that. So you could imagine that there is many ways to fit this picture. It's clear already here that we may have 2 different populations. Maybe this is a third one. I don't think we know. The problem is these kind of low masses. Okay, we get to see them much closer. We don't see enough volume, so it's not surprising that we haven't yet seen this one. This one is at that scale, but that's the only one. And this is a black hole with a companion matter star. Oh, sorry.
Why are there 2 strips like this? So just purple ones. Why are there just like a smaller strip and a bigger strip? Why is this gap?
It looks like there's 2 lines together.
These ones here?
Yeah.
I don't know. No, good question. I don't know what that one. So maybe I haven't covered it. So I'll show you a little bit of what happens. So 2 black holes. With 2 black holes, we don't expect an electromagnetic counterpart, and it's all sort of interesting stories of what much we can do if we have electromagnetic counterparts. With black holes, we don't believe at this stellar mass scales that we could have that such a counterpart. In the first detection, there was a paper, people claiming, oh, there is a counterpart. That mainly has gone away. In this latest paper, there is another one that says, we've looked, and there's nothing. So that keeps confirming the expectation. but we'll see. Suppose you now change one of the black holes or two. You have one neutron star or two neutron stars. What would we expect? Well, you already know what to expect, at least in this case. So with a black hole, we have these innermost circular orbits, and things can just fall into the black hole. But if this radius at which a star gets disrupted is farther from the black hole than the distance at which it falls in, you're going to disrupt it completely. So if the star gets swallowed whole, then you just have a black hole, and that gravitational wave will be exactly like the two black holes that you had. No, there's no way to tell them apart. If you disrupt a star, you're going to form a disk. If you form a disk, you have a black hole with a disk. And there are tons of ways of having electromagnetic counterparts, and we can talk about about this tomorrow. If you have two neutron stars, similar things can happen. You can form the two black neutron stars as they collide could form a black hole, or as they collide could form a hypermassive neutron star or a massive neutron star that lasts for a very long time. And this one you can begin to play the game of how do you set the different time scales. Remember the very first slide? Different channels will give you or give rise to some of these time scales if you can get to. So given that I think I'm out of time, I'm going to stop here, and I can show you some of this later. Let me just finish with this movie. This is a case where the star doesn't get disrupted till it actually crosses the the innermost circular orbit. And so it's just star goes around. The innermost circular orbit is this one. The event horizon is that one. It's going to disrupt once it starts falling in. But at that point, you're essentially just shutting off the whole thing. There is not enough cycles for LIGO to tell that case apart than two black holes of the same masses coming together. There's a little bit of a tail, but that would produce very little counterpart. So let me stop here. Thank you.
Like you were saying earlier, that the tidal effect was time orders. I guess I'm curious, like, you know, what kind, like, whether we could imagine two fairly realistic models of the state of a neutron star, like whether there's precision.
Yeah. Exactly. Thank you, because this is one of the slides I didn't get to. So we can show. These are just some waveforms of exactly that. You have three equation states of neutron stars that are consistent with nuclear models. They are consistent with observations, and then you ask, can LIGO tell them apart? If I show you the waveforms, those are the waveforms. I mean, you can see there are three lines. It's obvious that they are different. And then you can ask, is it obvious for LIGO that they are different? And the answer is no, because they only show that at late times. You begin to see them apart. This is the LIGO noise curve. And then here's the strain, the effective strain of the waveform. They're all on top of each other, except a very tiny bit. There is something. But it's not enough for LIGO with an individual detection to get out. So people have done calculations. If you actually just stay with this one, how many events would you need to actually tell the equation of state, or rather first the radius of the new star to within, say, 10%? So that you be able to distinguish the star that gave you a 13 kilometer, the equation state that gave you a 13 kilometer radius star versus a 15, let's say. For that, the estimates are you need of the order of 100 events. Given that we haven't seen anything yet, this is going to be quite a ways down the road. But that's why we're getting to be creative, and this is what I called for at the very beginning. If you think of other ways of going after a signal, and this is something, okay, we can try to dig something after the merger. We can try to ask what is the impact on possible electromagnetic counterparts, and you can begin to build a case, which will never be as good as getting a signal that is clean, but you can build a case that will bias towards one conclusion versus another. But this is something that is very much a very active field of investigation. Thank you.
So along similar lines, I guess it would be very hard for LIGO to measure alpha prime.
What is alpha prime here?
So string theory has this entire series
Oh.
of entire curvature correction.
Yes, we're going to get to that tomorrow. It will depend, but I think I'm going to give you the punchline of my talk tomorrow. I think it will be very hard, given what we know so far. But we're just starting. So, I mean, to put things in perspective, this is kind of poetic and rather kind of corny, but we're at a stage similar to Galileo pointing the first telescope at the sky. Anything will be after that. Or just think of Kobe 30 years ago when it took the first real picture, a very deep picture of the CMB. I mean, that's a very crappy picture when you put it next to Planck. So this is where we are. We're at the Kobe era. Eventually, we will get a Planck-like figure. And that one we can dig a lot deeper. Oh, primordial, yes, but not directly. So this will be like the bicep, right? So there is SPT, there is Euclid, there is a whole bunch of things that you go very deep in the CMB, and then to see if there is an E, a B tensor mode, and then by seeing if there is any rotation, you can infer where there is primordial gravitational waves there. There are some proposals, but these are detectors that weigh so much in pie in the sky that I think the realistic case forward is through the CMB.